frequent landslides due to heavy rainfall during the monsoon season, posing risk to infrastructure and public safety. Slope stabilization is essential, and this study explored the use of palm kernel shell ash, an eco-friendly and cost-effective material, to improve soil strength and stability. Various tests were conducted, including particle size distribution, specific gravity, Atterberg limits, shrinkage limit, and standard protected compaction tests to evaluate soil properties and the impact of palm kernel shell ash. The findings provide insight into palm kernel shell ash potential to enhance soil performance, offering a sustainable solution for slope stabilization and safer infrastructure development. The objective of this study is to determine the soil's particle size distribution, classify it using standard systems, and interpret its engineering properties, and then to calculate the specific gravity of soil particles using a pyranometer and understand their application in real-world structures. And then to determine the water content at which soil transitions from a plastic to a liquid state. Next is to find the plastic limit of soil and calculate its plasticity index for classification. And then to measure the shrinkage limit and longitudinal shrinkage of a soil sample. Last one is to determine the optimum moisture content and maximum dry density of soil for achieving effective compaction.
Okay, I will explain the method we use in our study to see how palm kernel shell ash can improve soil properties. For our preparation, we conducted the particle size distribution test to analyze the soil's gradation. We started by cleaning and weighing all the sieves and the bottom pan. The sieves were stacked in order with the number 4 sieve at the top and the number 200 sieve at the bottom, and then the pan placed underneath. We poured the dried soil into the top sieve, kept it, placed the stack on a shaker for 10 minutes. After shaking, we recorded the weight of soil retained on each sieve. This process helped us understand that the soil's particle distribution before conducting further tests. For the specific gravity test, we weighed the empty pyranometer and recorded it. Then we added 10 grams of dry soil to the pyranometer and recorded the weight again. We added distilled water, soaked the soil for 10 minutes, and applied a vacuum to remove air bubbles. After that, we filled the pyranometer with water, cleaned the outside, and weighed it. Finally, we emptied and cleaned the pyranometer, refilled it with only distilled water, and recorded the weight to calculate the soil specific gravity. Liquid limit test. We passed the soil through a number 40 sieve, air dried it, and mixed it with water to make a paste, which we covered to prevent moisture loss. The soil was placed in the liquid limit device, spread evenly, and a groove was cut in the middle. We turned the crank at 2 drops per second until the groove closed. Collected the soil from the groove and dried it in the oven. And then we repeated this process with different moisture levels to ensure accuracy. In the plastic limit test, we took a small portion of soil, mixed it with water, and rolled it into thin threads of 3.2 mm diameter using 90 strokes per minute. If the thread broke, we crumbled the soil, collected it, and dried it in the oven. And then we repeated this process a few times to measure the soil plastic limit. Okay, for the shrinkage 300 grams of salt with water to make a paste slightly wetter than the liquid limit. The paste was placed in a grease mold, leveled with a spatula, and left to dry at room temperature for 24 hours before being oven dried. After cooling, we measured the shrinkage, and if there was cracks or curling, we carefully reassemble the pieces to calculate the shrinkage limit. And lastly, for the standard Proctor compaction test, we prepared 10 to 15 pounds of soil, pulverized it, and passed it through number 4 sieve. Then we added 99% of water to the soil, mixed it thoroughly, and compacted in layers using a mold and a rammer at a steady rate of 1.5 seconds per drop. Once compacted, we trimmed the soil with the mold with the soil and collected sample to determine moisture content. This process was repeated by adding more water each time until the peak wet mass was reached. Assalamualaikum, my name is Muhammad bin Muhammad Bakri. My matrix number is 21557. So, I will present about result and discussion. First of all, we did test for particle size distribution for our soil. So, from the table and graph, the soil showed a well-graded distribution. It is suitable for construction due to better compaction and stability. Next, minor inaccuracy could arise from weighing errors, but the overall trend was consistent and expectation. So next, the specific gravity test. It is showed that our result, which is in range 1.21 until 1.4, it is lower than typical values, which is at 2.6 until 2.8. Potentially, it is due to organic matter or procedural errors, which is we cannot avoid from it. And next is specific gravity is vital for soil classification, compaction, and stability analysis. Then we did the liquid limit test, which is in Atterberg limit. So from our table and our graph, we can conclude that the moisture content values within range 42 until 46% indicated fine grained soil with high plasticity. Next, proper calibration and consistent procedures were critical to minimize variability. But in our test with our additive material, you have to add a lot of amount of water because our additive need to absorb water. So for next Atterberg limit, we did for plastic limit test. In plastic limit test, the plastic limit that we get was 2.8% with a plasticity index of 18.08, reflecting cohesive soil behavior. Next, variability in result could arise from rolling techniques or heat transfer from hands, emphasizing the need for glove. So for the last one, for test Atterberg limit, we did the shrinkage limit. In our table, we get the result, and the average shrinkage limit is 5.24%. This is indicated that moderate shrinkage behavior, essential for assessing soil stability in structure. Next, inconsistent in soil preparation and drying were identified as potential error sources. This is due to because we get the result for dry soil too late, so I think this is because of human error. So for the last test, we did the standard Proctor compaction test. So from the calculation and from the graph, we can get the optimum moisture content and maximum dry density, which is for optimum moisture content is 12.25 and the maximum dry density is 0.335. I think that's all for my part, so thank you.
Now we go to our conclusions. So I will start first with the particle size distribution test. The PSD test classifies soil based on particle size and distribution. Using the ASHTO classifications, the soil tested was well graded, combining fine and coarse particles. This grading ensures the soil can compact effectively, creating a stable foundation with minimal gaps. It's also to enhance the accuracy of PSD results, precise weighing, especially for finer sieve. So now we go to specific gravity tests. Specific gravity tests highlight the role of soil density and mineral composition in engineering projects. Low specific gravity values might suggest organic matter or procedural error, which is underlining the need for standardized method and careful handling. Next, we go to the liquid limit test. The liquid limit test revealed the water content range 42% to 46%, where soil transition from a liquid to a plastic state. This result helped assess soil consistency and behavior under varying moisture conditions. To ensure reliable data, repeated testing with the standardized procedure is essential. Similarly to the plastic limit test, the plastic limit test identified the water content which is 28.8%, where soil transition from plastic to semi-solid state. Techniques like uniform rolling and repeat trials enhance accuracy, providing valuable insight into the soil plasticity. Next, the shrinkage limit test measure a 5.24 shrinkage, which is indicating moderate shrinkage potential. Variability in soil preparation impact results, highlighting the importance of consistent mixings and precise measurements. Last, the standard Proctor compaction test examine the optimum moisture content and maximum dry density. Our results show coarse soils achieve higher densities. By using palm kernel shell ash as a stabilizer, improve soil performance, offering a sustainable solution for infrastructure development. It's also optimizing this process, minimize adverse effect, ensuring stable and eco-friendly designs.
In this slide, I will talk about the recommendations to improve the accuracy in each test. For the PSD test, we had cleaned the sieve and weighing equipment to avoid contamination. But for better results, we recommend to use more precise weighing equipment to reduce any small errors in fine soil particle measurements. In the specific gravity test, we make sure to use the distilled water for accurate results, but we could improve the accuracy by ensuring there is no air bubbles remain in the pitometer by using a longer working time. For the liquid limit test, we ensure a consistent drop rate of approximately twice per second. But to improve the results, we should mix the soil paste more uniformly before starting the test to prevent inconsistencies. In the plastic limit test, we followed the correct rolling procedure by roll the soil evenly with consistent pressure to form the threads of 3.2 mm of diameter. To improve the consistency, we recommend to keep the soil moist and cover it between the tests to avoid the premature drying of the soil. For the shrinkage limit test, we applied the petroleum jelly to the mold to prevent soil from sticking on the mold, and to achieve the more accurate results, we should maintain consistent oven temperature, which is in between 105 degrees Celsius to 110 degrees Celsius to ensure uniform drying. Finally, in the standard Proctor compaction test, we had filled the mold with soils in 3 layers, and we had compact each layer with correct number of blows, which is 25 blows. But it is important to control the moisture content more carefully to ensure the compaction process is uniform. For the general recommendations to achieve reliable lab results, the first is we must always repeat the test multiple times to check for consistent results and reduce errors. This will help to verify that the results are accurate and not influenced by outliers or random variations. It is also crucial to keep the equipment clean. The tools such as sieves, molds, and containers should be cleaned thoroughly between tests to avoid cross-contamination, which would skew the results. Besides that, we must use the accurate and well-calibrated tools. For example, we must make sure the weighing scales, sieve, or other equipment are precise and well-calibrated, as the errors happen here will affect the entire test outcome. Moreover, we also should handle the soil consistently throughout the testing process. This can be done by prepare and handle the soil in the same way each time. For example, we should wear the gloves to avoid changing the soil properties with heat from hands, and also we should wear the mask to prevent the inhaling of the fine particles. Next, we also recommend the accurate mixing of PKSA, which is the palm kernel shell ash, with the soil. This is to ensure the thorough and uniform mixing of PKSA with soil to avoid segregation and also ensure the consistent stabilization. Finally, we should conduct the test with different amount of PKSA. For example, we can add 2%, 4%, or 8% of PKSA into the soil, and then we can compare the results, and therefore we can determine the optimal percentage of PKSA for effective soil stabilization and also cost efficiency. In short, by following these recommendations, we can achieve more reliable results and get better understanding on the effects of PKSA on soil stabilization.